Alright guys, it's finally here. We are going to start our first new unit of semester 2. And we're going to start this new unit by looking at a new topic in calculus. So let's begin by reviewing what we did last semester. We spent the majority of last semester learning how to find slopes of functions at one point. We called these slopes derivatives, and we used them to answer questions about tangent lines, secant lines, normal lines, position, velocity, acceleration, graph sketching, optimization, related rates, and to make guarantees about functions using the EVT, IVT, and MVT. Now in this semester, we're going to change gears. In this semester, we will be learning how to find areas that are trapped between the graphs of functions and the x-axis. And we're going to use these areas in application questions later on. So for now, what we're going to do is focus on how to find those areas. So this sort of chapter is going to be focused on performing these computations so that we can learn how to apply them. So what is this area? What is this symbol? Well, just like first semester, we were focused on derivatives. Second semester is going to be focused on what are called integrals. An integral's notation looks like this, looks like kind of an elongated S. And here's what this notation means. This notation means find the area between this function and the x-axis starting at this x value and stopping at this x value. Now the dx here is the end of the notation. So it's kind of like, if you remember like parentheses, you need a parentheses at the beginning and a parentheses at the end. The opening to an integral is this integral symbol, and the end of the integral is the dx. They kind of provide a beginning and an end for setting up the problem. So, a visual representation of this would be, if the graph of this function is given, show what it means to find the integral from -2 to 3 of that function. Well, finding the integral means to find the area between that function and the x-axis starting at -2. So this is going to be my starting x value, and ending at +3. So that's going to be my ending x value. So what I'm going to do is I'm going to put a line here. That's the beginning of the area that I want. Now I don't really need to put a line here because it touches the x-axis there, but it stops there. And the area that I'm trying to calculate is this area right here. Now, just like in derivatives, negatives meant direction. So for example, if your velocity was negative, it just meant that you were traveling to the left. When areas are above the x-axis, so in other words, when they have positive y values, they are considered positive areas. But when areas are below the x-axis, in other words, when they have negative y values, they are considered negative areas. So in this picture, the area here would be considered positive, and the area here would be considered positive. But the area here would be considered negative, and the area here would be considered negative because it's below the x-axis. So how do we find these areas? Well, if I give you a picture and I say, find the integral from -3 to 0 of f of x, and the graph of f of x is shown. Here's what this problem is asking me to do. Starting from -3, which is here, ending at 0, which is here, find the area trapped between the graph and the x-axis. So I'm going to draw a line here, that's the beginning, and I'm going to draw a line here, that's the end. My first area will be this triangle, and then my second area will be the one that's below the x-axis there, so this triangle, stopping at the blue line. Now, because these are geometric shapes, they're triangles, we can use geometry formulas to get their areas. So the integral would be equal to, the first area is above, so it's going to be positive, and the area of a triangle is 1/2 times the base, which has a size of 1, times the height, which has a height of 1. Now I'm going to put a minus, and the reason I'm going to put a minus is that the next area is below. It's still a triangle, so the size of it will be 1/2 times the size of the base is 2, and the size of the height is 2. Now the reason I'm doing it this way is because the area of a triangle is 1/2 times the base times the height. I probably should have written that down earlier, but there you go. Now if I actually do these computations, 1/2 times 1 times 1 is 1/2, minus 1/2 times 2 is 2. Which means I have 1/2 minus 2, so -1.5, or -3/2 would be my final answer for the total area there. If I look at the next example, it says use the same picture but find the integral from 0 to 4. So 0 would be my beginning x value, and 4 would be my ending x value, and I want the area trapped between the curve and the x-axis, which would be this area. Now, I've made it red because since this part of the graph is below the x-axis, this area is going to be negative. And it's going to be a little bit complicated to find this area. A lot of students make a mistake here and think you want the area inside of this half circle, but because an integral is always computing the area between the curve and the x-axis, it would actually be this area. However, to find that, I have to do kind of a tricky thing. I have to imagine that this is a rectangle and that I took away that half circle. So in order to get the area, I'm going to do the area of the rectangle, which would be base times height. So the base would be 4 times the height would be 2. And I'm going to subtract, I'm going to take away the semicircle. So the area of the semicircle would be pi times the radius, which is 2, squared, divided by 2, because it's only a semicircle, it's not a full circle. Now if I actually do those computations, I'm going to have 8 minus 4 pi divided by 2 is 2 pi. And I have a negative here because, again, this area was below. So I'm going to make whatever answer I get here negative. Since 8 minus 2 pi is not something I can compute in my head, I can leave the answer like this, or I could distribute the negative. So I could have -8 plus 2 pi, and either one of those answers would be okay. Last but not least, let's see if we can find the area between -3 and 4. So -3 is here. 4 is here. I want all the total area between -3 and 4 in this graph. So I'm going to have this area at the beginning, which is positive because it's above. Then I'm going to have this area in the middle, this triangle. Then I'm going to have this area, which we just computed was the semicircle. Now, lucky for us, we actually already computed all of these areas individually, so we can use our work from the previous problems to figure this out. We said this initial purple triangle, which we figured out up here, had a size of 1/2. Since it's above, I'm going to make it positive. Then I'm going to subtract the size of the underneath triangle, which if we look back up here, we said had a size of 2. So 1/2 minus 2. And then I'm going to subtract the size of this area down here, which we said had a size of 8 minus 2 pi. And if I figure this out all together, I'm going to have 1/2 minus 2 minus 8 plus 2 pi. So 1/2 minus 10, which would be negative 19 over 2, plus 2 pi would be my total size of this integral. Let's look at a few more example problems. So sometimes instead of being provided with the graph, you're going to have to sketch a graph so that you can visualize what's going on and then use area formulas to compute integrals. So let's look at a couple examples where you have to sketch the graph. It's very helpful to have a straight edge for these so we can make a relatively accurate graph. So the first graph here is finding the area between -2 and 2 of this picture. Now this right here is a semicircle formula. And the reason I know that is because the equation of a circle is x squared plus y squared equals r squared, where r is the radius. So if you isolate y, you get plus or minus the square root of r squared minus x squared. So whenever you see a square root and it's just the positive, instead of getting the full circle, you just get half of the circle. So if I were to sketch this picture, I would draw the top half of a semicircle whose radius is 2. And the 2 comes from the 4. So r is 2 because 2 squared is 4. So I would have 1, 2, 1, 2, 1, 2. My semicircle would look like this. Now it says here I want to find the area on between this graph and the x-axis from where x is -2 ending at where x is 2. So in other words, this whole semicircle is what I'm interested in. To get that area, I would just do pi r squared, so in this case r is 2, divided by 2 because it's only half of a circle. So I would have pi times 4 divided by 2, which is 2 pi, and that would be my answer. In problem number 2, it says find the area of the underneath the graph 3. There's no x, just 3, between -4 and 1. So if you just have a constant, your graph is going to be a straight horizontal line. 1, 2, 3, 4, and -1. 2, 3, 4, 1, 2, 3, 4. So your function is going to look like a straight horizontal line at the +3. And you want to find the area between -4 and -1. Now once I graph it, I can see that that area just looks like a rectangle. So to find the area of a rectangle, I would just do base, which is 3, times height, which is 3. So I would have 3 times 3, which is 9. If I want to find the area between -1 and 4 of this piecewise function, it's going to be very helpful for me to sketch the piecewise function. So I'm going to make a graph. So it looks like the breaking point for the piecewise function is at the +2. To the left of the positive 2, my function is just a straight horizontal line at positive 2, and it ends at a closed circle. So the left side of my graph is just going to look like this. Now the right side of my graph is going to be the line y equals x. So at positive 2 it's 2, 3 it's 3, 4 it's 4. So it's going to be a diagonal line that looks like this. If I want to find the area between this graph and the x-axis from -1 to 4, I can see that this is more complicated than just a straightforward shape like a semicircle or a rectangle. Instead, I'm going to have to break this up into two shapes, and I'm going to find the area of this rectangle first and then add in the area of this trapezoid. So let's work on the rectangle first. The rectangle is just going to be base times height, so 3 times 2 plus the trapezoids formula is 1/2 times the height. Now the height of the trapezoid here is actually sideways because the two parallel lines are these two lines, and the height is always the distance between those parallel lines. So the height is 2, base 1 is 2, plus base 2 is 4. So the area of a trapezoid, by the way, in case you forget, is 1/2 times the height times base 1 plus base 2. So it's a good formula to remember. So now if I do some computations, I'm going to have 6 plus half of 2 is just 1, so 6, and then that gives me a total of 12. Last but not least, the next problem is a very common problem and a very common graph that comes up in calculus, and it's the absolute value of x over x. Without going into too much detail, because we have seen this graph before, what we need to know about this graph is whenever you have the absolute value of x over x, whenever the x's are negative, so it's the left of the 0, the function's value is -1. It's a straight horizontal line. And whenever you're to the right of the 0, the function's value is a +1. It's a straight horizontal line. That's just something we've talked about before that you definitely need to know in order to be able to do a lot of these problems. So it's a good graph to remember. -1, 1, and 2. So if I want to find the area between -1 and 2, again, this is a little more complicated because part of this area is below and part of this area is above. So let's start with the below. Because it's below, I'm going to make the area negative. Because it's a square, the area is going to be 1 times 1. Plus, because it's above, I'm going to make the area positive. Because it's a rectangle, I'm going to do base times height, so 2 times 1. So I'm going to have -1 plus 2, which is +1. All right, I know this was a bit of a longer video, but we are introducing one of the main ideas for all of second semester. So I think it's worth it to take our time and to really make sure we understand what an integral is and how to find these areas. We will definitely be practicing this in class tomorrow. Thank you so much and have a great night.